Scale farmers operating outside these enterprise networks face a different reality. Without automation, they rely on manual, reactive methods that lead to significant resource waste, particularly the overconsumption of water and electrical power during environmental fluctuations. However, the underlying principles of smart farming, early disease detection, and resource mitigation can be executed using off-the-shelf microarchitectures rather than high-cost proprietary hardware. This creates a unique engineering challenge, integrating the unpredictable behavior of organic biology with the rigid, binary requirements of automated digital systems. Improving the sustainability of small plot agriculture requires translating enterprise-level automation into localized, closed-loop microsystems. A rigorous model for this approach was presented at the 19th Indian edition of the Concours Fête de la Science competition. Students at the NSC Bose Govt Girls Higher Secondary School in Thalatheru, Karaikal, developed a systems engineering project designed specifically for this localized scale. Their project, an IoT-based disease detection and mitigation system, provides a framework for autonomous crop management. The system targets two functional goals: the early mitigation of plant disease and the implementation of smart irrigation cycles based on real-time field data. This infographic outlines the project's smart monitoring cycle, mapping the data flow from the physical plant and its environment through the processing unit to a remote monitoring interface. The system utilizes optical leaf color analysis as a primary diagnostic tool. By tracking the shift from green to yellow, the sensors identify biological stress markers without the need for complex, invasive testing.
Good morning to one and all present here. This is Yashmi studying in 9th standard from the student of NSC Bose Government Girls High Secondary School. Today I talk about IoT-based disease mitigation for smart agriculture. First, let me discuss about what is mean IoT. IoT standard for Internet of Things or Internet of Technology that connect a device to Internet automatically. In agriculture, IoT helps the farmer to monitor crop, soil, temperature and water level using a smart sensor. Thus, the system saves the water, reduce the manpower and increase the crop production.
Demonstrates how low-cost components can form a highly effective, decentralized decision-making matrix for agricultural use. Building this autonomous matrix begins with the physical assembly of the hardware layers. We can map these layers onto a digital schematic, starting with the foundational grid for the system components. Phase 1 establishes the input matrix. These sensors are responsible for gathering the raw telemetry required for autonomous control. The first vector tracks subterranean moisture. A specialized sensor measures hydration levels at the root zone to prevent over-irrigation. The second vector monitors the atmosphere. A DHT11 sensor logs ambient temperature and humidity, providing context for the evaporation rates in the field. The third vector serves as a biological proxy. A TCS3200 color sensor is calibrated to monitor the light reflectance properties of the plant leaves. Optical color detection provides a low computational method for identifying nutrient deficiencies or pathogen stress. The system uses the shift from green to yellow as a high-fidelity indicator of early-stage plant disease. This synchronized telemetry matrix effectively translates the physical variables of farm into a structured digital data stream. Once the telemetry is digitized, the system must determine the appropriate environmental response. This occurs in Phase 2, central processing. An Arduino or ESP32 microcontroller functions as the logic engine, executing pre-programmed Boolean conditions as it parses the incoming sensor data. If soil moisture levels drop below a programmed percentage, or if the biological proxy detects yellowing in the leaves, the logic engine triggers a mitigation sequence. This sequence initiates Phase 3, output and actuation. The relay driver is the essential component in this final stage of the circuit. In this architecture, the relay acts as an electromechanical bridge. It allows the low-voltage logic signal from the microcontroller to safely trigger high-voltage hardware components. This triggers the primary mechanical response. The relay activates a DC sump pump and solenoid valves to deliver water directly to the stressed plants. Simultaneously, the system executes secondary outputs, updating a local LCD display and transmitting field status via Wi-Fi to a mobile device. The integration of the relay driver creates the physical connection necessary to transform environmental monitoring into active, closed-loop intervention. Validating this theoretical model requires analyzing its performance under actual field conditions.
This is the team leader, Yashni. This is our project. I am going to demo of my project.
3.
The first sensor is soil moisture sensor. Soil moisture sensor check how wet or dry the soil. Next, temperature and humidity sensor. Temperature and humidity sensor monitor the weather condition. Data is sent to the cloud. All this data to their network like Wi-Fi, 4G, LoRa, etc. to the cloud platform. The cloud analyzes the data, decide whether irrigation is needed. Take automatic decision. If the soil is dry and it's not rainy, the system decides to water the plant. If the soil is moisture or rain is expected, it skips the irrigation. Sensor is leaf color sensor. Nowadays leaf are getting so many diseases. We didn't know why it is happening. If you take leaf from your plant and keep on the leaf color sensor, it analyzed by the RGB color. The microphone will be tell you, and we also see on the display.
Your plant is healthy.
தண்ணி வர மாதிரி காட்டிக்கலாம்ல.
Monitoring and control. The farmer can use a mobile app or a website to view weather data. First, temperature, Fahrenheit. Next, humidity level. A third, temperature, Celsius level. And a fourth, soil moisture level. They can manually turn off on the system from anywhere. Next, I am going to check here this yellow color leaf.
Your plant is having magnesium deficiency.
The yellow color leaf have the magnesium deficiency.
5-day observation table tracks automated responses. Days 1 and 2 show a stable baseline, with moisture between 78 and 82%, and light green foliage. On day 3, temperature spikes to 92 degrees, and the leaf color shifts to yellow. This data state breaches the logic engine's threshold, identifying a deficiency that requires immediate correction. Between day 3 and day 4, the microcontroller activates the relay, firing the DC sump to irrigate the field and mitigate the detected stress. We can see the results of this automated intervention by analyzing the data from days 4 and 5. Moisture levels have been driven up to 88%. As a direct result, the biological indicators recover, with the leaf color sensor returning a reading of green. Provides clear economic advantages by reducing crop loss through early detection, stabilizing yields, and lowering manual labor costs. There is also a critical environmental impact, as this type of precise automation promotes the sustainable use of water and energy resources. The architectural strength of the project lies in its accessibility. It achieves these high-precision results using affordable microcontrollers rather than enterprise-level server infrastructure. Ultimately, this systems engineering approach shows that the efficacy of smart agriculture depends on the precision of the logic engine rather than the footprint of the infrastructure.
Thank you.